This conference will now be recorded.
Hello everyone. So in this video, we will discuss previous year's questions, and that is from the exam NEET, and this is from the chapters Hydrocarbons. Here we have the first problem, identify product A in the following reaction. So here a carbonyl compound is given because in this compound two ring structure is there. One is benzene ring, another one is normal cycloalkane, and here we have COCH3 group present, right? We are treating it with the reagent zinc mercury amalgam concentrated HCl. We are getting A and 2 molecules of water. We have to identify product A. Now it is true that some carbonyl compounds are given and we are discussing previous year's question from hydrocarbons. But here based on the final product, basically I have chosen this problem. Okay. So here what is the effect of this reagent on carbonyl group, that we have to know. So this is the reaction that is actually happening here. Clemenson reduction reaction, where if you have some carbonyl group, both side you can see alkyl groups are there. It may be cyclic structure also. That means if these two parts can be connected also. But important point is here, whatever changes are happening, it is at this part, C double bond O. So this part is now converted to CH2O. So if you are treating it with this, what will happen? This C double bond O group, these two groups both will be converted to CH2. So the first option, it is not correct because here you still have OH group. Second option, you also have OH group, right? And this one is also not correct because here total number of carbon 1, 2. Here also 1 and 2. Carbon number will not be lost. As you can see from this general reaction structure, it is not that some carbons will be lost. So carbon number will remain same. So that is why the last option will be the correct option. Fine. This is the structure of A. Next question is, identify the final product D obtained in the following sequence of reactions. The first starting material given is acetaldehyde. You are treating it with lithium aluminium hydride acidic condition. We are getting A. Second reagent is H2SO4 heat. We are getting B. Then HBr we are getting C. And in the last step, now probably you can understand from the reagent sodium diether, and there is some halo related compound. It may be haloalkane, it may be haloarine, but whatever. From this type of reagent, it is clear what type of reaction it can be. Sometimes what happens when you have this type of question from the reagent, you have to recognize what is the reaction that can happen. So this is a specific reagent, right? So there are some reactions that are where you will have some specific reagents, and from the reagents you have to recognize. So basically this final step is Wood's reaction, where two alkyl group, or it may be one benzene ring or benzene derivative, is attached to some another part. And another important point is, as in the final step you are using some benzene related compound, so it is normally you can expect that in the final product also, that is in the D, there must be some benzene structure, isn't it? Because this part, as what we are using in the last step, that must be present in the final product. Now if it is so, then option 3 and option 2, these two cannot be correct. Now if it is 1 and 4, in 1 there are 2 benzene rings, but in 4 there is 1 benzene ring. So probability is that 4 will be the correct answer. Though it is not the, I'm not saying that it is the right way to solve the question, but if you are in a hurry, this type of logic if you can apply, then also you can choose the correct option. But here we will see the details. Here option 4 is basically correct, and this part is coming from, that is how you will understand quickly. This part is coming from the final reagent, which is bromobenzene. And look at this part. In this part you have 2 carbon. So these 2 carbon is basically coming from the first reagent. And why that is carbon numbers are maintained? Because other reagents, if we look carefully, these reagents are not such where carbon may be lost. So that is the reason option 4 probability is high. But obviously it is better if you can write all the reactions. We are using here reducing agent, RA, reducing agent. So it will be converted to CH3, CH2, OH. From aldehyde, now you will get alcohol. Now this chapter is that is this question is also related to the oxygen related compounds chapter, that is carbonyl compounds chapter. But most of the question you will get here a mixture of different units ideas you have to apply, right? So here hydrocarbon concept is also there, then oxygen related compounds, that concept also we have to apply. Next reagent we are using H2SO for heat. So this reagent it is for dehydration. So when there is dehydration, because this is alcohol, you will get CC double bond. Once you get CC double bond, that is B. This is your structure A. This is B. Now with B you are treating it with HBr. So this is simply HBr addition to CC double bond, and you don't have to think about which side it will go because it is symmetrical. So H2C Br, and this side you have CH3. So it is ultimately bromoethane, CH3 CH2Br, and finally you are treating it with PHBr in presence of sodium triether. So what will happen? This part and this part will be connected, and Na will be removed along with these two bromine. So that is the role of Na here. So what will happen finally? pH will be now connected to pH CH2CH3 ethyl benzene. So final product, that is the final option, is the correct product structure. Fine. Choose the correct sequence of reagent in the conversion of 4-nitrotoluene to 2-bromotoluene. So what is 4-nitrotoluene? 4-nitrotoluene we'll start with, and we'll try to apply all the reagents one by one so that we can choose which one is actually correct. 4 position CH3 and another position that is NO2. So this is 4-nitrotoluene. Now suppose if you are following option 1, why it is absolutely not possible? Just from the first reagent you will start, you will not be able to proceed, because when you are applying NaNO to HCl, this reagent is specifically used when there is NH2 group. Again, see this question you have to have some knowledge of some other groups, that is nitrogen containing compounds, when there is amine, when there is NO2. But here that is toluene structure is there, so that is why this question I'm discussing under hydrocarbon. So here when you apply NaNO to HCl, NO2 group there is no reaction. In NO2 HCl, it is specific reagent only for amine, especially aniline. So look at this reaction. This is actually Sandmeyer reaction. Sandmeyer reaction, you can see some examples. So in Sandmeyer reactions, we take aniline or aniline derivative. You treat it with HX NaNO2, mostly HCl NaNO2. Temperature is very, very low, 0 to 5 degree, around this type of temperature. You get diazonium salt N2 plus X minus. Now this diazonium salt, this is intermediate, it is not very stable. Depending on what type of reagent you are treating it with, you will get different types of products. So when you take CuX, where CuX is either Cl or Br, it is not I, then you get halobenzene. So this group is completely replaced by X. If you use Ki, you get adobenzene. If you use CuCN, Cn is there. If you use aqueous H2OH is there. Similarly, when you use H2O or H3PO2, sometimes simply H2 is mentioned or simply H3PO2 is mentioned, then this group is basically converted to hydrogen. That example is not here. So here the 4 reactions that you are seeing there, these are different examples for Sandmeyer reactions. So here NaNO to HCl, the first reagent we cannot proceed, so this is we can cancel. Now the second option, what you can have, if you start from nitrotoluene, 4-nitrotoluene, first you are treating it with SnHCl. So when it is SnHCl, this is reducing agent, NO2 will be converted to NH2. Now the next reagent you are using Sandmeyer reagent. Now what will happen? This part it will be converted to N2 plus Cl minus. Next reagent is bromine. Now when you are having diazonium salt, normally we treat it with this type of reagents. But bromine, if you add, it will not affect here, right? And what will happen after bromine addition? You can think that bromine will be added to ortho position of methyl group, and then we are using H2, H3PO2, so that this part is converted to H. Now that will reach, you can reach correct answer, but that is not the ideal way, because whenever you have formed N2 plus, this is not very stable. The next reagent must be such where this N2 plus should be replaced by some specific group. So that is why this is also not correct. Now what will happen if I use option 3? Option 3, you are treating it with bromine. So when you are treating it with bromine, here NO2, with respect to NO2 group, the position you will not select. You have to select the position of Br with respect to methyl, because methyl is activating. It has plus I effect, but NO2 is deactivating. So, and it is electrophilic substitution. So that is why with respect to methyl, you have to understand what will be the position for Br. Basically, Br will be inserted here. So you have already reached your answer, because you have to make 2-bromotoluene. You just have to remove this part. Next reagent is SnHCl. That means I am just simply writing this part, because rest of the part there will be no change. Then you are using Steinmeier reagent. That means N2 plus Cl minus will be produced, and then you are using H2H3PO2. So what will happen? This part there will be simply H. Now I can write the full reaction. Fine. So N2 plus, it is simply replaced by hydrogen, and you are getting 2-bromotoluene. And what is the problem with the last reagent? Last reagent, if you first start with SnHCl, what you get? You get NH2. And next you are using bromine. Now NH2 is activating, CH2 is also activating. NH2 is basically more activating, because it has not just a plus R effect, which is stronger than plus I effect. Now what will happen? Bromine will be as if it will be controlled by NH2 more. That is, its position will be selected by NH2 effect. But that is not right, because now bromine will be added, and it is so activating. Sometimes 2 times ortho position bromine can be added, but that is not desired. So that is why, keeping all the factors in mind, we have to choose the third option, right? Identify X in the following reaction. You have started with 1 mole of benzene ring, where 1,4 position you have chlorine and bromine. You are treating it with magnesium in presence of dry ether. Now this type of reagent combination, it is obviously for Grignard reagent preparation. Now the question arises that I have a benzene ring where both sides there are 2 halogen. Now with which halogen you will actually make the Grignard? Now basically it is the bromine CBr bond. In between these two, Mg will be inserted, not CCl, because Br is CBr bond breaking. It is comparatively better than the breaking the CCl. So that is why when you are treating it with 1 mole of Mg dry ether, see here it is specifically mentioned 1 mole. So it is magnesium, and the benzene derivative ratio is 1:1. So it is not that both sides you will make MgBr and another side you will make MgCl. No, it is not that. It is 1:1. So specifically Mg will be inserted towards bromine side, and you will get BrMg. Rest of the part there is no change. So this is the intermediate, and finally you are treating it with D2O. Now D2O is just like water molecule, only a difference is H is replaced by the deuterium. Otherwise there is no difference. And in Grignard reagent, this is the carbon metal bond. So this part and this part, there is some negative character, and here we have some positive character. So this part, it will act as if it is a base, and it will capture this D. That means there will be D will be attached to the benzene ring where originally MgBr is present. Now you will get this type of product, and the fate of the rest of the parties, you will get Br, Mg, Od. So it is deuterium substituted chlorobenzene, which you will get from option 1. Now, why the other options are not correct? Because this type of product is absolutely nonsense. It is not possible. You can easily cancel this option. Now, if you made the mistake that both sides, if you are making MgCl and MgBr, then you can choose option 3 as by mistake. But as it is 1:1, 1 mole, 1 mole, you have to take care of this fact. This information is important. And option 4 you will choose if you by mistake make on the towards the chlorine side. If you make the Grignard reagent, then Br will be as it is present in the benzene, but that is also not correct. It is the CBr bond through which Mg will be inserted. So this option is the correct option. Fine. decreasing order of boiling points of the following alkanes. Now, when we decide boiling point of alkane, we have to take care of two facts. The first fact is, what is the carbon number? Because with increase in carbon number, molar mass increases. And when molar mass increases, van der Waals interaction also increases. And when van der Waals interaction increases, that means intermolecular interaction is becoming stronger. Then from liquid phase, when you are trying to move towards vapor phase, it requires more energy. And that means boiling point is high. So boiling point, it is directly related to the molecular weight. Now this is one factor. Now when you have same number of carbon, now another factor you have to take care of, and that factor is whether branching is present or not. So first, with increase in carbon number in a boiling point increases, and in case of isomeric alkene, that means when carbon number same, greater is the branching, lesser is the boiling point. So branching and boiling point inversely related. Now come to the question. Option A, heptane. So you have 7 carbon, butane 4 carbon, 2-methyl butane 5 carbon, 2-methyl propane again 4 carbon, hexane 6 carbon. Now if you simply focus on the carbon number, A should be having maximum boiling point. After that it should be E, because 6 carbon, 7 carbon, 6 carbon, next is 5 carbon, that means 2-methyl butane. So C should come at second position, right? And after C, now you are stuck between B and D. Both are for C, for carbon. But in which case you have branching? You have branching to methyl propane. That means it should have least boiling point. So after E, we have to write B and then D. So it is matching with last option. So whenever that is alkane you have and boiling point related question, just check first total carbon number you have to identify, and the next thing you have to see that whether branching is present or it is simply linear chain. So in these two molecules, basically we have applied the second factor, and for the first three we have applied the first factor, right? The products A and B in the following reaction. So different types of structures for A and B are given in option 1, 2, 3, 4. Now I will suggest when you get this type of question, don't look at the options at all, because sometimes looking at the option it may mislead you. So if you directly look at the question only, whatever reagents are there, and just solve it in your own way, and then you can check whether it is matching with these options or not. So here we have pH, then CC double bond. The first reagent you are using HBr. Now we know when we add HBr to CC double bond, Markovnikov rule is we have to take care of. And again, I will say that don't blindly follow Markovnikov. Just check yourself at what position carbocation is stable. So when you add hydrogen to the terminal position, you get positive charge at the carbon which is next to pH. And positive charge next to pH is very stable because this positive charge can take part in conjugation with the double bonds of benzene ring. So that is the reason Br will be added to the next position of pH. And that is also according to Markovnikov. So this is the product you will get. Next, you are using Mg dry ether, which is Grignard reagent. That is this type of reagent we use when we make Grignard reagent. So you will have now MgBr. Next, you are using CO2. Now CO2, it will act as electrophile here, and what will happen? As I have said, this is carbon metal bond. So this part always reacts as if it is a base. But in this case, no question of base because you do not have any acidic hydrogen. So it will now act as nucleophile. So as if this part is nucleophile, this part is positive. So as a negative charge, you can imagine as if it is here, though it is not fully generated negative charge. I am just saying it so that it helps you to do the mechanism. So this negative charge, it will attack here and double bond will be shifted. You have H2O plus in the medium. So ultimately what will happen? pH, C double bond O, O minus will be there, but because of this H3O plus, ultimately it will be OH and methyl group. And this part, you don't have to think about, this will be the byproduct. Now, because in the medium you have water, so it can make MgBr OH type of compound. But whatever, you just have to focus on this. This is your A, and it is matching with what? It is matching with option 2A, isn't it? Now, this structure is not given in any other options. So, isn't it enough to, that is until this point, it is enough to choose which option correct. Even if you are not drawing what, you are not writing the mechanism for B, then also we can say it is option 2. But here obviously we will see what is happening. SOCl2. Now, whenever you have any acid, suppose you have acid RCOOH, you are using SaCl2. The function of SOCl2 reagent is that OH is replaced by chlorine. So it is as if chlorinating reagent for acid. Okay, not R. pH, CO, Cl, this part CH3. Next you are using MEnH2. Now MEnH2, this lone pair will attack here and Cl will be removed. NH, Me. You can think that this H and Cl together, it is removed in the form of HCl. So this is the final product. pH, CHMe, CHMe. So see, it is matching with this one. Then CONHMe, right? Option 2, correct option. The incorrect method for the synthesis of alkenes. Synthesis of alkenes. Which method is not correct? Treatment of alkyne. So suppose we have any alkyne like this. You are treating with sodium, liquid ammonia, and this reagent is specifically we use when we want trans addition of H. But we don't have to think about trans or cis. You will get alkene, that is sure. So this is not correct option because we are getting alkene. Heating alkyl halide with alcoholic KOH. So suppose you have some alkyl halide RCH2 Br. You are using alcoholic KOH. So when you use alcoholic KOH, it is very important. It is not aqueous KOH, it is alcoholic. Let me write here CH3 because I need some beta hydrogen. So this is alpha position with respect to Br. This is beta position. So beta position hydrogen and this Br, it will be removed. And ultimately you will get CH2 double bond CH2. So alcoholic OH we use when we want to remove HBr. This is also correct method. What about 3? Treating alkyl halide in presence of aqueous KOH. So let me take the same alkyl halide again. When you are using aqueous KOH, now this Br, that will be replaced by OH group because now you are using aqueous KOH. You are not using alcoholic KOH. That is the difference. The role of KOH, it is different when the medium is aqueous or the medium is alcohol. So it will be substitution product. It is not that HBr will be removed. So this is actually the incorrect method. Okay, so option 3 is correct. But what is the problem with 4? Vicinal dihalide. Vicinal dihalide means at 1 and 2 position you will have some halo. And this side any group. Now when you are using zinc, as if these two Br along with zinc, together it will make Z and Br2 and you will get double bond. This is also a method for alkene preparation. Only the third method is giving you substitution product, not elimination product, and that is why it is not the correct method for synthesis of alkenes. We'll go to next question. The correct structure of 2,6-dimethyl DEC-4-ene. Now DEC, even without looking at the option, simply write the structure directly because it is not that you can also look at the structure, you can decide. But I think if you simply draw the structure and try to match with which it is matching, it will be better. DEC means 10 carbon. So simply write a parent chain having 10 carbon. Put numbers. 2 position you have methyl group. 6 position you have methyl group. And your position of the double bond is at 4. Now just compared with the structures given, you will see In between the two methyl group, you have total 3 carbon. Now, between two methyl group, you have 3 carbon. You have 2. This is not possible. 3 carbon, possible. 3 carbon, possible. 3 carbon, possible. Now, look at the position of double bond. From the terminal position, after a methyl group, it is at 4 position. That you are getting 1, let me change it. 1, 2, 3, 4. But we have already cancelled it. It is 1, 2, 3. So 3 position double bond. It is 1, 2, 3, 4, 5. And even if you are moving from the other side, it is also 1, 2, 3, 4, 5. So this is not possible. So from this logic, we can choose option 1 as the correct option. Fine. Next question is the major product of the following chemical reaction. Here we have CH with 2 methyl group. The reagent is HBr, but what is this one? PHCO whole 2 O2. This molecule, if you write it properly, PHCO coming 2 times, and in between this you have peroxide linkage. Now, whenever you have any peroxide linkage containing compound and you are doing addition of HBr, it will follow anti-Markovnikov rule. That we know. So this is the role of this reagent, and anti-Markovnikov rule means if it is carbon number 1, this is carbon number 2, it is unsymmetrical alkyl. So the negative part of the reagent will be added to that carbon which is containing higher number of hydrogen, and carbon number 2 is basically containing higher number of hydrogen. So that is why the negative part that will be moving towards this side. Now if you apply this according to this explanation, look at the options. First option, the reagent itself is added. It is absolutely not possible. Then look at the option 2. In option 2, keeping the basic structure same, the double bond is removed, but bromine is added to carbon number 1. So it is according to Markovnikov, not anti-Markovnikov. So that is, it is wrong. Then option 3, Br is added here, as if there is some rearrangement taking place, and then it is possible. So suppose if you are not using oxide linkage containing compounds, you are adding HBr, then there is a chance of carbocation rearrangement. How it will happen? So first carbocation will be here, and then this is secondary carbocation. If this hydrogen is replaced here, new carbocation will be here, and then this type of option 3 compound possible. But that is not happening here. But the last one is actually the correct option, because from this molecule, ultimately you will get the H will be added here and Br will be added here. So this is according to our anti-Markovnikov, and last option will be the correct option, right? And why here no question of rearrangement? Because this mechanism is through radical mechanism, and that is why there is no question of this type of rearrangement. Fine. I'm not saying that radical rearrangement that doesn't take place, but here that will be not happen. And when you use peroxide compound and you are adding HBr, it is anti-Markovnikov rule. It is only applicable for HBr, not HCl or HI. Then the main difference is when you do not use peroxide, first H is added to the alkene, you get some carbocation, and then Br minus is attached to the carbocation. But when it is not according to, that is when it is in presence of peroxide, first Br dot radical that will be added, and when Br dot radical is added, the first compound you will get, first radical you will get this one, and then it will take H dot from HBr. So in this way we get the final compound. Fine. So this is the option, correct option, option 4. An organic compound contains 78% by weight. Suppose total weight of the molecule, if it is X, then 78% of this total mass, suppose X gram, then 78% is the mass of carbon. Remaining percent is that of hydrogen, because it is that means it is hydrocarbon. Otherwise, why it will be mentioned like this? Now, the right option for the empirical formula of this compound. Empirical formula means that is the simplest formula. Suppose if I consider CH empirical formula, with this empirical formula, you can have molecule C2H2 or you can have C4H4. That means always the ratio of C and H, it will be 1:1. Similarly, if you take this empirical formula, the structures that are possible, the simplest structure possible is obviously methane. Another possibilities are C2H8, carbon and hydrogen ratio, it has to be 1:4. So that is the principle of empirical formula. Similarly, from this empirical formula, you can get C2H4, you can get C3H6. So carbon and hydrogen double. The ratio is 1:1, 1:2. So we have to choose which empirical formula is correct. Now, when it is mentioned that 78% by weight, that means it is almost 80%. That means 80% is coming from carbon and 20% is coming from hydrogen. So the ratio of carbon and hydrogen mass, that must be, that is, I'm not talking about number, I'm talking about mass. That must be 4:1, right? Now, don't think, when I'm saying 4:1, I'm saying that it is C4H. No, that is not the case. It is in terms of mass. Now, consider the options one by one. If it is option 1 carbon, that means 12, and 2 hydrogen, that means it is 12 and 2 gram. 1 carbon atomic weight 12 and hydrogen 1. So it will be basically 6:1. This is not matching with our 4:1. So this is not correct. What is the option 2? Carbon 1, so it is 12, and 3 hydrogen, so it is 3. Now this is leading to 4:1 ratio, isn't it? So it may be correct option. We'll also check the other. Here we have 1 carbon and 4 hydrogen. So this is leading to 3:1. Right? Now, what about the last option? Last option is 1 carbon, 1 hydrogen. So it is 12:1. So taking care of all the factors, this should be the correct option. Right? So 78, it is almost 80. This assumption you can do. CH3, and this is the empirical formula. Major product formed in dehydrohalogenation reaction of 2-bromopentane is pentene. So this information is clearly given. Now this product formation is based on which rule, that you have to understand. So first write the structure. 2-bromopentane, 1, 2, 3, 4, 5. And from this, you are getting pent2-ene. So this is the position of double bond. Now here basically this hydrogen is removed. This is the beta position with respect to bromine. And this is according to which rule, that we have to answer. Now this is obviously not correct. It has nothing to do in this chapter. It is all about in the atomic structure, right? Then Hoffman rule. These two rules basically related to this question. Huckel's rules is also not related. Option 1 and 3 easily we can cancel. Huckel rule is related to aromaticity. And here we are talking about elimination reaction. HBr is eliminated. And this is with respect to bromine alpha position. This is one beta position. This is another beta position. So here, this beta position, we have removed the H and we are getting pent2-ene. This is according to iitjee rule. So when you get this type of highly substituted internal alkene, then it is according to iitjee. But suppose if you are removing hydrogen from this beta, then you get double bond at the terminal position. And this is not internal alkene, and it is less substituted. Why less substituted? Because in this alkene, you just have one alkyl group. But if you consider this one, it is highly substituted because you have two alkyl group, and that is according to iitjee, and this one is according to Hoffman. And depending on the structure, what type of reagent you are using for HBr removal, depending on that, sometimes we get Hoffman product according to Hoffman rule, sometimes we get iitjee product according to iitjee rule. But in general, most of the time, Sedgwick rule is applicable because ultimately your product is more stable. Internal alkenes are more stable than this type of terminal alkene. So answer should be option 4. Which of the following alkane cannot be made in good yield by Wood's reaction? So in Wood's reaction, what we do, we take one Rx, another Rx. Now these two are maybe different or may not be different, but mostly it is takes same. So when it is taken same, this part is removed and you get RR linkage. But suppose if it is prime, now there is several possibilities. It may be that between two, suppose you have taken one Rx, you have taken one R prime X. So in that case, you will get reaction between two R prime X and two R prime will be connected, or it will be reaction between one R prime and one R. So three types of possibilities will be there when it is unsymmetrical alkyl halide you have started with. But why I am discussing this? What is the relation with this? Here for this question, cannot be made in good yield. That means you can get it in a very less amount of yield, but good yield you will never get. Which reaction? Which alkane? So Wood's reaction we use here, as you can see, CC linkage, CC bonds are prepared. That means we are getting butane. Now when it is N-butane, that means it is 4 carbon. So you can start from this type of alkyl halide. So when this is removed and this is symmetrical, N-hexane. So this is also symmetrical. So from this part, that is 3 carbon fragment, this is 3 carbon fragment. Then what about the option 3? 2,3-dimethyl butane. So this is 2 position, this is 3 position. Again it is symmetrical. So you can start from this type of alkyl halide compound. In between there is 2 sodium. This will be connected. But the problem with the last one is N-heptane. Now it is 7 carbon. So you have to start with, suppose one side you have 2 carbon, another side you must have 5 carbon. Now the problem arises. It may be 2 carbon, you can take 5 or you can take 3 or 4, but you cannot take even number both sides. So it will be unsymmetrical alkyl halides. You will start. Now the problem is when you have this type of R, suppose one is Rx, another one is X R prime. So problem will arise. Different types of compounds will be there, and you have to separate the actual desired product. And separation is also difficult because all are alkane and their boiling points, melting points are very close. So this is a problem. Even if you are getting the desired product, it will not be very good. So unsymmetrical alkane, if you want to make, Wood's reaction is not a very good method. So that is why this is the correct option. An alkene on ozonolysis gives methanol as one of the product. You have to find its structure. Now methanol what? Methanol is C double bond O, HCOH. This is methanol. That means whatever if your structure of alkene, one side suppose I do not know, I am simply writing, another side must be this type of fragment. So from this side basically you will get CH2O, that is methanol or formaldehyde. Now come to the options. If you break this CC double bond, you cannot get methanol because you do not have double bond CH2 fragment. Similarly, this is not possible. This is not possible. Only the last one possible. So from option 1, basically you will get C double bond H2 from one side, and from other side you will get this one. But you are interested in this part. So that is why this option should be the correct option. Fine. The most suitable reagent for the following conversion. Here we have internal alkyne and the final product is cis-2-butene. Okay. So when it is hydrogen addition, basically you are adding hydrogen and that is also from the same side. So when it is same side addition of hydrogen, you are getting cis-2-butene. Specific reagent you have to use. If you are using the first reagent, it is sodium liquid ammonia, you get basically trans structure. So this is not correct option. But when you use, this is the second reagent, which is a linear catalyst. Here the reaction will give you a C addition, and ultimately it will lead to cis-2-butene. So second option is the correct option. What is the role of this reagent? Zinc ZnHCl basically we use. Suppose you have alkyl halide, that is you have Rx, and this X you want to replace by H. That is basically you are making alkane. Then ZnHCl can be used, which is as if supplying the hydrogen atom in place of X. But this is not the reagent we use here. Then what is the role of this reagent? H plus water, that is acidic aqueous medium in presence of Hg2 plus R. So here we get basically hydration reaction. So what will happen? You have CC triple bond, and there will be addition of OH group, that is net addition. I'm just talking about the final product. Detailed structure mechanism I'm not talking about. So if CH and OH are added, you get CC double bond and H. And then it is having some enol structure, there will be conversion to ketone. But it will not give you cis-2-butene. It is basically addition of OH group and H group, net addition of water. But that is not the reaction here. So that is why option 2 will be the correct option. Okay. Among the following, the reaction that proceeds through an electrophilic substitution. Now, electrophilic substitution and benzene ring is given. So, general mechanism for electrophilic substitution, what happens? First, there is some E plus. Then these double bonds are attracted to this E plus. One of the double bond is broken. There is carbon E bond and positive charges here. Next, there is some counterpart of this electrophile or some other reagent. What happens? Finally, this H is removed. So there is CH bond formation, and finally you get the aromatic ring back, and E is here. So it is H replaced by E. Now here the first reaction is Sandmeyer reaction. You have already seen this. And Sandmeyer reaction, it has nothing to do with the double bonds of benzene. It is simply this group is replaced by Cl. Okay, direct this replacement, but it is applicable for the second, because here Cl2 and AlCl3, the role of AlCl3, it is Lewis acid, it will take one of the Cl and itself will be converted to LCl4 minus, and the other chlorine will be Cl, and this is actually our E plus. And then you just have to follow this mechanism, general mechanism that I have written, and you will get final compound like this where E is Cl. So this is actually the correct option. But why the other options are not correct? The third option is you are doing this in presence of UV light and all the double bonds are gone. So it is basically addition reaction. It is not substitution reaction, right? So no question on substitution. Then here for the last one, the whatever changes are happening, it is happening at this part. Carbon OH group is replaced by Cl. So this is basically as if OH group is removed, and this C, it is not electrophilic substitution, it is basically nucleophilic substitution. This Cl minus, it will attack here, which is the nucleophile, and OH group will be removed. First OH will be converted to OH2, which is a good living group. So this is basically nucleophilic substitution, and that is happening outside the benzene ring. But electrophilic addition mechanism you can get only in option 2. Fine. So this will be the correct option. And this is the last question we'll solve in today's video. An alkene A on reaction with, this is ozonolysis reagent, you are getting propanone. Now propanone is this molecule. Another part is ethanol. Now ethanol is in equimolar ratio. Ethanol means 2 carbon aldehyde. So these are the products you are getting. So when you have this type of product, then addition of HCl to A gives B. First try to understand what is A. If you connect this part, you get this type of molecule. This is our A. Now when you are treating it with HCl, this is unsymmetrical alkene. That means negative part will be added to this side where less number of hydrogen present. So this is your B as the major product, because the minor product is where Cl is added to the other side. Anti-Markov conversion. Structure of B you have to find. So structure of B is Me2 CCl and then CH2, CH3. So Me2CH, Me2CCl directly linked. It is matching with option 3, isn't it? So this should be our correct option. So first you have to do ozonolysis reaction, and this ozonolysis, basically the product of ozonolysis are given. You have to move backward and you have to identify what is alkene A. Once you know the alkene A, then only you can proceed what is B, and B structure is given in the options. So option 3 is the correct option. So that's all for this video. We'll end the session here. Thank you for listening.